Hello, welcome to session number 30 in the series Analog Circuit Design using ADS. My name is Anurag and continuing from session number 29 where I design a 12-bit accumulator, right? I'm going to design a compensation network and complete a MASH 111 sigma delta modulator. So I need few more blocks. First block I would need is a half adder. So I'll make a new schematic called HAD. And this half adder is very simple. All I need is a XOR gate for the AND operation and a NOT gate, an AND gate, sorry, an AND gate followed by a NOT gate. Okay, so this would be my half adder. So all I need is a VDD, a ground, and then I need two inputs A, and then I need B, and then I would have a sum as the output, and then I would have a carry. So I will put this as a carry. Okay. Okay, so that's a half adder. And sorry, this has to be a NAND gate. Okay, so that's a half adder. And we already have a full adder. So let me just make a symbol for half adder. And just to make sure that I know this is a half adder, I can put here uh, a text which is HA. Okay, Next thing, I want to do a slight modification of a MSD latch, where instead of Q I want a Q bar output, correct? Because I need to do some form of a subtraction, right? Okay, so I need to take the MSD latch, which is over here. I also want to do one thing. I want to create a version without the reset, right? Or without the clear. So first of all, I'm going to say new or copy cell, and I'm going to copy this to sigma delta or to here itself transmission gates, and I will say no CLR. So there is no CLR on this one, and all I need to do is I'm going to throw off this guy. And there is no need for this one then. So the clear terminal would be gone. So this one is without a without sorry without a clear. Just bear with me a second. Okay, and moreover I would need a Q bar on this. So that's going to be Q bar, correct? And I'm going to rename this as Q bar or QB, and then I'll modify the symbol for this. In this case, the clear terminal would be gone, and instead of Q I'm going to have QB. Okay, and similarly I'm going to add this to reflect QB. Okay, so this is going to be MSD latch with the Q bar output without a reset. Okay, then I want to make another version where I would bring out a negative output. Okay, so I'm going to copy this cell, and instead of drawing from here I will draw from here, rename this as QB, right? Okay, so the next thing is, so this is with the negative output Q bar, right? And so this is terminal number 5. So I will go here and change this symbol. Hang on. Yeah, so this symbol would be, this will be called Q bar, and here is also Q bar. So this one is with the Q bar output, right? Okay, so we have all the ingredients to make a difference cell. So I'm going to first make a difference cell. Okay, so just bear with me a second. Okay, so what I'm going to do is I'm going to take 3 for 3 bits. So let's make that. So I'm going to make here new schematic. I'll call this as differentiator. Okay, so in this case I'm going to take a MSD latch with a bar output, Q bar. So that's that one. So for 3 bits I'm going to have 3 of these. And then I'm going to have VDD ground clock and A0, A1, A2. So let's do the pins. VDD, then I'm going to have a ground, and then I'm going to have A0. Over here I'm going to have A0, sorry, and then I'm going to have A1, and then I'm going to have A2. So as simple as that. A0, A1, A2, and then I will name this VDD and ground. So I'm going to name this as VDD, this as VDD, sorry, this one is ground, so this is VDD, this is VDD, and this one is ground, and this is ground, and this is ground. Okay, so all my grounds are connected. Okay, and then I'll connect all the clears together as one. Okay, so just brought this up here. So what do we have? We have these carry bits, right? So these carry bits C0, C1, C2, they are going to go through this network. So what I need to do is, first of all, I will be subtracting, right? But then subtracting a delayed copy of it. So basically, as we were adding a delayed copy with Z minus here, we'll be subtracting a delayed copy. So what I need to do here is, in this, first of all, I'm delaying it. So that is Z minus here. So I'm doing this first Z minus here. I'm delaying it. So I have this D flip-flop, right, where I'm delaying it. Okay, the next thing is, I am, instead of taking a Q out, I'm taking Q bar. So that is going to be the ones complement. So basically this word, which is A0 to A2, I'm doing a delayed copy by Z minus, and then I'm doing a ones complement of this, right? So that's clear. Okay, so let's just put in more things in here, uh, like the clock and the clear, right? So for clock, let's put a pin here. Okay, so this clock, I am going to go and given through a set of buffers. So if I take a NOT gate, right, so I'm going to put 2 NOT gates here, back to back. So that's going to buffer my clock, so that this stage doesn't load the clock. Okay, so here I am going to name the node VDD and ground. Sorry. So that's VDD, this ground. Okay, and then this is going to drive the clock. Okay, and then you have got the reset or the clear, right? And that's going to be driving this, right? So okay, so now these are all connected. Then I'm going to take this Q bar out, and then I'm going to put through a half adder. So I am going to put through half adder because there I'm doing one's complement, so I don't have another word. I'm just going to add 001 to do two's complement, right? So I'm going to take a half adder here, right? And this half adder will receive, so these half adders are going to receive the inputs. So one of the inputs is going to be VDD. So this is one. So you remember you do one's complement and then you add one to it, right? So that's what I'm adding one to it, right? And then this is going to be driving, sorry. Okay. And then let me connect ground first so that I don't forget that. Ground, ground. And then I have this one like this, and the sum is going to move on, and the carry is going to go in as a B, right? So I don't have a second word here, so I'm going to use carry as B, correct? And then this is going to receive this one, and then I am going to, so I don't need another carry. I just need a, because this is just a number where I want to add 001, so I just need a XOR gate for another AND. I don't want to waste a AND gate in the half adder, so I'm going to just go ahead and put a XOR gate here. So that's going to do the last bit AND operation. Okay, again there's going to be VDD and ground. So this is going to be VDD and this is going to be ground, right? And one of the inputs is going to be the carry out of this one, right? And the other input is going to be A2. Okay, so now at this point I need to bring in A. Okay, so I'm going to do a difference with the delayed copy, right? So I need A0, A1, A2, and then the output of these, okay, going to full adders, right? So I need full adders. So I need a full adder. I need 3 of these. 1, 2, and 3. Again, I'm going to connect VDD and ground first so that I don't forget. So this is VDD, VDD, and VDD. And then I've got ground. Sorry. Ground, ground, and ground. And here, the first carry. Okay, so first one needs not be a full adder. It can be a half adder because there is no carry in here, right? So I am going to put in a half adder instead of a full adder. And here, this I'm going to remove. Okay, so here I don't have a carry, right? So what I'm going to have is one of these outputs and then A0 output. So that's A0, right? Okay, so then the carry of this one will go as a carry in of this one. Okay, and then this one will receive this and A1, correct? So this is going to receive A1. Okay, so the last one is going to receive the carry of this one, carry out of this one, right? Let's see if it allows me to do it here. Okay, so the carry out of this one goes to C in here, and then this one is going to receive this and also a copy of this. So basically I'm subtracting the previous version of A0, A1 and A2 from the current version of A0, A1, A2, right? And the output is going to be, so here okay, here this one is useless, right? This carry is useless, right? So here I'm just going to do I'm just going to leave it floating. So instead of leaving it floating, I'll just do a lumped component termination into 5 femto. So this is going to be 5 femto. So because this is useless for me. Okay, and then what is useful for me is D0, D1 and D2. So I have D0, D1 and D2. Okay, so I hope you understood what I did. And this is equivalent to this block, right? This and this. So there will be two of these, right? Two of these blocks would be there. Okay, and they will be cascaded again, right? Like this. So this is entire compensation network. So let's do the remaining part, right? So this is called the difference circuit. So I'm just going to make sure this difference circuit is okay before proceeding further. So what did I do? I took D flip-flops with the bar, so that's going to do one's complement, and then I did a half adder with 001 addition, so that gave me 2's complement, and then the 2's complement I added with the, so this is the delayed copy of A0, A1, A2, so I did a delayed copy sum with A0, A1, A2 to give D0, D1, D2, so that is equivalent to this Z minus and then this C2 bar summed with C1n, right? So that's that. Okay, so having done that, I am going to make a symbol for this one, right? Okay, so let's go to the differencing circuit. It's not differentiated, it's a differencing circuit. So I'm going to make a new symbol for this. Okay, so I have got A0, A1, A2 as one side and D0, D1, D2 as the other side, and then the clock and the clear at the bottom, I can put it on the side, doesn't matter. So I'll put in clock here, and then clear and the ground at the bottom. Clear and ground. Okay, and just to remind me that this is going to be a hash triggered negative, I add this one and I add a small bubble here. So before that, let me just do this. So this is a difference, 3-bit differencing, where the delayed copy of A0, A1 or C0, C1, C2 is going to be subtracted from C0, C1, C2. Okay. Okay, so let me add a bubble to this. Okay, so this is done, and I'm going to just exit this. Now I'm going to put together this entire compensation network, and I need 2 of these differencing circuits, right? Okay. Okay, A2. Okay, so let's put this together. So I am going to make a new schematic, and I will say this is comp 3 bit. So this is a compensation network 3-bit. Okay, so first thing I'm going to have is a differentiator. Okay, and I'm going to create 2 pins somewhere. Okay, so one will be VDD, and the other one will be ground. Okay, so here, okay, so this one is ground and this one is VDD. Okay, so this is out of the way. Now I am going to have A2 bit. Okay, so now I am really implementing uh, this. Okay, so I'll take one of the bits, the other bits are going to be 0, right? So I am going to take A2 bits as A0, A2 bit over here, and the remaining is going to be grounded. Okay, okay, and then I am going to drive this with a clear and a clock, right? So I'm going to have a clock over here. So this is driving that, and then I'm going to have a clear. Right. So now I'll bring the A1 bit through a half adder, and D0, D1 and D2. So I'll have a half adder, two half adders and an OR gate. Okay, so I'm going to bring in two half adders and an OR gate. Something which is similar inside the differentiator, right? So it's like this. Okay, like this, two half adders and an OR gate. So all I need is these three blocks. Okay, somehow it doesn't accept. Control C, Control V, Control V. Okay, so what do we have here? Okay, we have got A1. Okay, let's place it here. Okay, and this is simple. So C out of this will be, because there's nothing much here, C out of this will be going here, and the C out of this will be going here. So I don't want to leave any confusion, right? And then this one is going to have D0 from this one to here, and this will be A1 bit. So I'll introduce A1 here. Correct. And then this one is going to be D1, and this one is going to be so this is that way. And then I'm going to do a delayed copy of that. So basically I'm over here at point 2. Okay, and I want to do a delayed copy. So means that I want over here I want MSD latch but without inverted gates, right? So I have to be here, right? Okay, so I'll put in MSD latch. MSD latch. So this is MSD latch with the Q output, right? So I want that, and I want 3 of them. Okay, again I'm gonna do VDD and grounds. And I'm going to have a clear signal here. So this being done, I need to connect the clear signal. So that's a clear signal for all of them. Correct. And then I'm going to have a clock. So for the clock, I'm just going to introduce 2 delay networks here and then introduce a clock. So I'm going to put 2 NOT gates. 1 again this will be VDD, this will be VDD, this will be ground, and this will be ground. Okay, so this will still be a clock network, and I'm going to give this two clocks. Okay. Okay, so this is paired with clock, and their outputs I am going to go as inputs. Okay, so here I'm at point number 2. Okay, and then again I have to do differencing. That means okay, so that means that I have to again introduce this block. So I'm just gonna copy this block here, and here I'm gonna remove this one, and here the clock is coming from, so just hang on a sec. Okay, so I'm going to introduce 2 more buffers here, the same buffers over here. So this is still a clock, and I'm going to drive this clock with that. Correct? And then the clear is going to be the clear, right? So the clear would remain clear here. So that's the clear bit. Okay, and then these are the 3 inputs, A0, hang on, A1, and A2. Okay, and its output I'm going to give to half adder, full adder, and full adder, right? Okay, so I am going to introduce here another D flip-flop, MSD flip-flop with no clear. Correct? And then I'm going to have VDD and ground. And then I'm going to bring in A0 bit here, and this is going to be clocked by this. Okay, so I'm going to bring in A0 here. Okay, so I am going to bring in A0 from here. Okay, and then I'm going to give it to a set of half adder, full adder, and full adder, right? So I have half adder. Okay, so I'm going to put in here a half adder, a full adder, and a full adder. Okay. Okay, again I'll put VDD and ground first. VDD and ground. Okay, to this half adder, I'm going to receive the input of this D latch, right? So that's a delayed copy. So I'm going to receive the input of this D latch. And then I will have the other input coming from the difference circuit, D0, right? And then this carry out would go in as a carry in. Okay, and to this full adder, the input is going to be the input is again going to be this D0 bit, which is delayed copy, and this one. Okay, and finally the carry off out of this will go as a carry in of this guy. Right, and then one of the inputs is again going to be delayed copy of A0. Delayed copy of A0. And the other input is going to be D2. Okay, so having done this, okay, I have got some from all of this, and I'm going to clock it out with a register. For the register, I'm going to use a MSD latch, correct? So here, same as these, right? One, two, three. Okay, and I'm going to clock it with a buffered version of clock. Okay, so this is all to take care of the clock distribution. So I'm not going to talk about clock distribution here. So that's the delayed copy of the clock. And this clock is going to clock all of these. And this is also going to have reset, which is going to be all combined, right? So just bear with me. Okay, so that will be that clear only. Clear? Clear. Okay. And these outputs, some outputs will go to the D0, D1. Okay. And this will be terminated into 5 femto because I don't need that. So I'll just copy this one. Let's just terminate it. So don't worry about that. So all I'm going to have here is D0, D1 and D2. Okay, so I have input as A0, A1, A2, and my output is D0, D1, D2, and then I have got clock and I have got clear, right? And then I have got two more pins, which is VDD and ground. Okay, so this completes my compensation network, which is shown over here, right? So I'm going to put this mesh 111 sigma delta together and see if it works. So first thing, I'm going to make like a symbol for the compensation network. Okay, and let me just simplify some stuff here. Okay, so I have a clock and a reset, ground A1, A2, A3, A0, A1, A2, D0, D1, D2. So I'm going to put these at the bottom because they are going to come from the accumulator A0, A1, A2. Then I'm going to have the output. So let's move this to the side. I'm going to have the output over here as D0, D1, D2, and the supply is at the top and the ground is at the bottom. So supply is at the top and ground is at the bottom. And clock is to the left and clear is to the left. Okay, and all I can do is, if I want, okay, now one thing I can do is I can remind myself that this, hang on a second, that this is edge triggered with a negative edge. Okay, so all I'm going to do here is going to put in a edge symbol for that. and then I'm going to put a bubble here. Okay, so I'm done with the compensation network, and I am going to put together the sigma delta modulator. So for that, I'm going to make a new schematic, call this as mesh 111 SD sigma delta. Okay, so here I am going to need 3 accumulators. So I am going to put 12-bit accumulator. So one more thing I want to do here is I want to take this off. Okay, the remaining block remains the same. Okay, fine. So I'm going to put 1, 2, and the third one is without the output, 3. Correct? Okay, so as simple as that. Okay, and all of them seen is going to be grounded. Okay, so I'm going to create 2 pins, VDD and ground. Name this as VDD, name this as ground. So this is a ground, this is a ground, this is a ground, and the carries are also grounded, right? So this is a ground, this is a ground, and oh, I need the one with the ND here. Okay, fine, and that's the ground. As simple as that. This is going to be VDD. Okay, and then I'm going to bring in the compensation network. Okay, in case of compensation network, VDD and ground. Okay, so this is VDD and this one is ground, right? And then you are going to have A0, A1, A2. So this carry out would be A0, this carry out will be A1, and this carry out will be A2, as is over here C0, C1, and C2. Similarly, you have A0, A1, A2, and then the reset or clear. Okay, so the clear is going to be common between all of them, right? Okay, so I am going to have two more pins. One is clock and clear. Okay, and then these pins will be uh, fine feed, right? So I will call this as, okay, so first I'll put these. So this is going to be fine feed. So I'll put F0, F0, F1, F2, F3, F4, F5, F6, F7, F8, F9, F10, and F11, right? So F0, F1, F2, F3, F4, F5, F6, F7, F8, F9, F10, and F11, right? And then I'm going to have clock and clear left, and this is D0, D1, D2 are the outputs. Okay, so D0, D1, and D2 are the three outputs. D0, D1, and D2. So all that is remaining is going to be connecting the clock and the clear, right? So I will create two more pins. One will be called clock, other will be called clear. And here I'm going to put in two sets of two buffers. So I'm going to go in here. So there will be a lot of buffers here I can copy from. So I just want to copy these two. Edit, copy, edit, paste. So one set is over here, second set is over here. Okay, so this is clock and this is clear. Okay, so all I'm going to do is first one, I'm going to apply the clock and clear from here. So this is your clock and this is your clear. Right? Okay. The second one I'm going to provide from here. Okay, so this is your clock and this is your clear. And the third one is very simple. This is your clock and that's your clear. Okay, so here I'm going to introduce clock and clear from here to the compensation network. So this is the clock and this is the clear. Okay, so that completes my sigma delta modulator, and I'm going to make a symbol for this one, right, and then test it. So just wait. Okay, so I'm going to make a symbol for this sigma delta modulator. Okay, so for this sigma delta modulator I am going to have F0 to F 15 on one side, and clock also here, and clear at the bottom. So that's the clear, and the ground at the bottom. That's the ground. And VDD at the top. Okay, so I'm just going to write a piece of text here saying that this is a sigma delta modulator. Here I want to put a edge trigger. And introduce a small bubble here. Okay, so that's a sigma delta modulator. And I'm going to test this sigma delta modulator next. Okay, so my mesh 1 is okay. Now let's test it if it was really working. Okay, so I'm going to say test mesh 1 1 1. Okay, so first thing I want to bring in is this sigma delta modulator. Okay, and I am going to put here a load. So I'm going to put here, so I'm going to copy the stuff from other test cells, right? So let's say if we tested something like anything, test accumulator, right? Okay, so I'm going to copy from here these three, and then the process, the transient simulation, the supply, and the 0 and 1 bits, and probably this one. I'll copy all of this stuff. Control C, Control V. Okay, so I am going to have D0, D1, and D2. So I have then I'm going to have supply, and then I'm going to have ground, right? And then here I'm going to feed in some random number and figure out if this comes out to be a value. So here, as far as the clock and the clear is concerned, right? Okay, so I am introducing a delay, and then I'm operating at 100 megahertz. So this is the same stuff. So this is your clear, and I'm introducing a delay of 5 nanosecond here. So this is your clock, and let's not do a delay of 5. Let's do a delay of 4 itself. So with the delay of 1 nanosecond, it will introduce a pulse of 2 nanosecond, and on the 4th nanosecond I am going to start clocking this, right? So let's put here some random numbers of zeros and ones. So we should make a note of what this is, right? So let me put here a piece of text. Insert text. So I'm going to check for a 12-bit number, which will start with, let's say, 0 1 1 0 1 1 1 0 1 1 1 1. How many bits are these? These are 12 bits, right? 1 2 3 4 5 6 7 8 9 10 11 12. So I'm going to start with putting in here 0. So what does this represent? So let's take a calculator, and let's look at a programming calculator. Okay, and let's put in here a hex number. So the hex number is going to be 6E and F. Okay, so 6E and F, I want to see in terms of decimal is this 6E and F. So this is 6E. Okay, so now that we have a sigma delta modulator, and this sigma delta modulator basically has a compensation network, and I added some buffers in here, right? So remaining, I didn't make much changes to it. Other than that, everything remains the same. So I have a 12-bit accumulator here, right? So there are 3 12-bit accumulators doing integration, and then there is a compensation network which is doing the differencing, right? And the output, what we expect is going to be between so this is a unsigned output. So what it means is it's going to have a DC value of 3, right? And then it will be between 3 and 4, any fraction which you put in here. So for example, here I have put in 0 1 1 1. Okay, so let's write this down. So insert text. Okay, so I have put in here 0 1 1 0 1 1 1 0 0, sorry, 0 1 1 1. Okay, so this is equivalent to, in a hex number, it's equivalent to 6EF. Okay, so this is going to be 0x6EF. Okay, in decimal, this is going to be equivalent to 1775, right? And the total number of cycles, so total number of states in the, it's total number of states for this sigma delta is going to be 2 raised to n, which is 12. So 2 raised to 12. Okay, so this would be equal to 4096. Okay, so now what is going to generate? So if I take a mean of D0, D1, D2, so the mean of D0, D1, D2 would be, so let me write it out here. Okay, so mean of this binary number which I'm going to generate, D2, D1, D0. Okay, over this complete cycles is going to be equal to 3 plus 1775 divided by 4096, right? So in this case this will be equal to 3.4333, right? And this is not going to be very accurate because I'm just doing the mean of these bits. Okay, so let's see how do we do that. Okay, so I'm going to simulate this for 5 microsecond only, though it has to be simulated for something like 40.96 microsecond to have the final value. So if I'm close to this number, I'm assuming that this is working, right? So what I'm going to do is I'm going to put you to pause, right? I'm going to put you to pause and then run the simulation. So let's run the simulation here. Okay, so once it's done, I'll come back and then we will see what the results are. Okay, so now we are done with the simulation for 5 microsecond, and let's plot some waveforms. These waveforms are going to be D2, D1 and D0. Right, so let's expand that and let's split it out. Okay, so this is what D0, D1, D2 are doing. And let's see a binary representation. So let's say a crude value, a crude way to do the value would be D0 divided by 1.5. So it's normalized to the supply plus D1 normalized to again supply, but it is scaled with 2 plus D2 normalized to supply but is scaled to 4, correct? So that's going to be the value of the 3-bit board, right? And let's put it here. Okay, so instead of these, let's delete those. I am going to put in here the value. Okay, so the values, you can see there are certain spikes here, which if I do a crude averaging, that spikes would basically do and mostly the spikes are up, right? So these spikes are going to give me a wrong value of mean, but it will be close to what I'm desiring. That's what I expect. So in a digital system, the system won't respond to these spikes, right? Okay, so that means that I want to find out the mean of the, so I can say mean value would be the mean of the value, correct? So this is a very crude method to validate this. Mean value is mean of the value, correct? And let's, okay, is this capital mean? No. Okay, value spelling is wrong. VALUE, typing error. And this is VALUE, correct? So the mean value is going to be expecting to be close to what I desire. So it's right now 4.6. So if I simulate longer, it will come down to 4.333, right? So that's what I expect, but I don't have time for doing this, right? So I'm going to leave this session. I'll end this session over here. But what this sigma delta is doing is generating numbers between 0 and 7 so that the average lies between 3 and 4, right? That's the whole idea. and that number would be added to your course feed, right? So the DC value is 3, and then I can generate any value between 3 and 4, and that will be added to the course feed, and that will constitute the final feed to the multimodulus divider. So to sum this up, I designed a sigma delta modulator, which is 12-bit, and it operates at around 100 megahertz. So for 80 megahertz crystal, this is going to be okay, right? And it has got 3 accumulators, or 3 orders of integration. So first order, second order, and third order, and the carry or the overflow bit goes to the differentiating circuit, and this is the differentiating circuit, this is the differentiating circuit, and the remaining is just, implementation of what we covered last time. So let me just go back to, okay, so it's basically doing this compensation network. So this bit is delayed by z minus 1, and that's being subtracted. Okay, so that's the manipulation over here. Y2 is equal to C0n, Y1 n, 1 minus z raised to minus 1. So that's going to be 2. And then again I do the operation. So I have Y2n is going to be C0n, C1n into z minus z raised to minus 1 plus C2n to 1 minus z raised to minus 1 square. Okay, so this is the sigma delta modulator. So this ends session number 30. Thanks a lot. Thank you.